Let's do some graphing. We're going to graph some rational functions with tables. And what's a rational function? A rational function is a function that has a ratio. Notice that rational has the word ratio built into it. You don't have to box that in, but there you go. We're going to complete the table of values for the function below. Sketch a graph, including as many points from the table as possible. We might have some that may run off the graph, but we'll see. State any x values where there is a discontinuity. What's that? And determine if the discontinuity is removable or non-removable. What in the world? Okay, we'll talk about that when we get there. Let's just figure some things out. A lot of this is going to be common sense at first. 6 over any x value I give you. So 6 divided by negative 12, well, that is negative 1/2. Okay? 6 divided by negative 10. Well, 6 over 10 is, well, 6/10. So negative 0.6. And then 6 over negative 8 is negative 3/4. Okay? 6 over negative 6. If you want to stop writing this side, that's fine with me. Negative 1. And then we're going to have 6 over negative 4. That's going to give me negative 1/2. 6 over negative 3 is going to give me negative 2. 6 over negative 2 is going to give me negative 3. 6 over negative 1 is going to give me negative 6. Okay. Okay, notice what's happening here. The numbers are getting, I would say bigger. They're getting more negative. They're getting a greater magnitude of negativity as we get closer to 0. 6 divided by negative 1/2. How many times does a half go into 6? Well, if you had $6, you would have 12 half dollars. We are dealing with negatives right now, though. Let's see, 6 divided by negative 0.25. You had $6. How many quarters would you have? You would basically do 6 times 4, and that would give you 24, negative 24 in this case. And then we're going to do 6 divided by negative 0.1, and that's going to give me, okay, if you had $6, how many dimes would you have? Well, 10 of them for every dollar, and you have $6, so that's going to be 60, technically negative 60. These two numbers are definitely going to run off the graph. We won't be able to plot them. That's okay. All right, we're going to have 6 divided by 0. Whoa! You just punched a hole in the fabric of the universe. This one is undefined. All right, let's pause right here, and let's go back up to the directions and talk about what this is going to be like when we get there. State any x values where there is a discontinuity. Discontinuity is, here's a rough definition, is where you stop graphing. You're forced to stop graphing and pick up your pencil. Now, it might be a situation where you have a piecewise function where there is a discontinuity where you'd be like, oh, look, it stops here and it starts back here. That's a discontinuity. Or you might have a situation that we're about to encounter where the actual x value is undefined. You can't divide by 0. So then in that situation, you would say, well, you know what? There's a discontinuity there too. Again, we'll talk about removable and non-removable in a minute. All right, and now we are on the opposite end of everything we've just done, and I don't want to waste your time writing the same things over and over, but 6 divided by 0.1 is 60, but we're on the positives. 6 divided by 25 cents would be 24, and then 12. 6 divided by 1, 6 divided by 2, 6 divided by 3, 6 divided by 4, 6 divided by 6, 6 divided by 8, 6 divided by 10, and 6 divided by 12. Okay, and we could go even further if we wanted to, but we're running out of graph. All right, we're going to plot these points, and when we do, you're going to see this really cool rational function. And we're going to just talk about what it looks like, what it deals with, what we're looking at, really, and the fact that this is undefined right there. That's weird. Okay, we're going to plot every one of these points that we can reasonably plot. So negative 12, comma, negative 1/2. Negative 10, comma, negative 0.6. Okay, so just a little bit lower than negative 1/2. Negative 8, and then negative 0.75. It's going to be right there. And then negative 6, negative 1. Notice a slight curve right there. Very slight, very subtle. All right, negative 4 is negative 1.5. Negative 3 gives me an output of negative 2. Negative 2 gives me an output of negative 3. Okay, a little bit of symmetry there. And negative 1 is going to give me a negative 6. Negative 1/2 is going to give me negative 12. And then as I get closer to the x-axis, I get further down, way further down. So if I did plot negative 0.25, I'd go about right here, and I'd go way yonder down here, and we'd be super close to the y-axis. And I might have said x-axis a second ago, but we'd be super close to the y-axis, but would never actually touch it. So then if I go to negative 0.1, just barely off the negative end, barely on the negative end of the y-axis, on the x-axis, then I would go down to negative 60. I'd be way, way, way down here. All right, so I'm going to do my best to connect these and not make it look terrible. So let's connect. It's got a little bit of a curve to it. Okay, I do want to keep going because this will never, ever, ever touch the y-axis. And actually, if I keep going this way, it'll never touch the x-axis either. So that is the first half of it. All right, let's graph the other half of it. So 0.1 is 60, so 0.1 way up here off the page. 0.25 is 24, still off the page. 0.5 is at 12. 1, 6, 2, 3, 3, 2, turn in the corner there. 4, 1.5, 6, 1, 8.75, 10.6, and 12.5. All right, let's connect those as well. Do your best to make it pretty. I have to turn my paper to get this just right. It's going to start a conversation right here. Drawing, I didn't want to mess up. Don't cross the x-axis, don't cross the y-axis. No matter how far out you would have drawn it, don't cross them. That looked like it crossed. Be careful. Okay, that is your very first rational function you have ever drawn. By the way, it is its own inverse. Just wanted to say that. If you were to draw the line y equals x and then reflect it across that line, you'd get the exact same thing. So sometimes a function is its own inverse. For real, like if you had y equals 6 over x, which you do, and then you switch x and y and solve for y, you'd get y equals 6 over x. It would be the same thing. So now we have to really do what it asks. We've got that much. We're going to state any x values where there's a discontinuity. So the only x value we were not able to really deal with was x equals 0. And then determine if the discontinuity is removable or non-removable. So let's slide up for a second, switch colors, and there is a, okay, I'm about to say removable or non-removable, discontinuity at x equals 0. All right, let's talk about removable and non-removable fill in this little gap that I left in my sentence. You ever driving down the road and you hit a pothole and you're like, man, that just hurt right there. Just a little pothole. Let's do that graphically. Man, there's a pothole. Like one dot that's missing, one spot. Boom. One spot missing. It's very jarring. That's removable. All you got to do is come along with some asphalt, fill that thing right in, solved. Got it. It could be a graph that looks like this. That's not, let's ignore that one. It's open circle here, but that other circle would be down here. Still, easily fixable. Take your point, move him up, you're good. But if you have a situation like this, not so easy to fix that, is it? So you basically like driving off a ramp or something. That is a non-removable discontinuity. And so in the situation that you have with the graph we just drew, we have this crazy rational function, so whoop, and then whoop, that is severely non-removable. You could say it's an asymptotic discontinuity, but that is a non-removable discontinuity. I'd love to give you a definition, but I'd prefer to give you examples. You will see examples of both removable and non-removable discontinuities in the next problem that we do.